A Saturn V is the most powerful machine humans have ever successfully operated. 33 engines on the first stage alone, 6 million pounds sitting on the pad, enough thrust to shake windows 15 miles away and register on seismographs. It is also for the purpose we are about to discuss, a toy. Here is the arithmetic that makes that word fair. Voyager is the fastest object we have ever sent out of the solar system, moving at about 38,000 miles per hour. The nearest star is 4.2 light-years away. At Voyager's speed, that trip takes roughly 75,000 years. Not 75 years, 75,000. Human beings were still sharing the planet with Neanderthals the last time 75,000 years went by. And Voyager has been flying that whole time. It launched in 1977 before the personal computer, and it has been moving away from us continuously ever since, for 49 years without stopping. In all that time, it has discovered roughly one light day. Proxima Centauri is more than 1,500 light days away. Voyager has done about 1/1500th of that trip, and it took the entire lifetime of everyone watching this. And that number does not improve much with better rockets, which is the part people find hard to accept. Build an engine twice as good and you have a 37,000-year trip. The problem is not that our engines are weak. The problem is that every rocket ever built has to carry its own propellant, and propellant has mass, and mass needs propellant to move it. That loop is called the rocket equation, and it does not negotiate. Past a certain point, adding fuel makes things worse rather than better. For 60 years, the serious proposals have all tried to break that loop, and almost all of them are enormous. Antimatter, fusion drives, ships that detonate nuclear weapons behind themselves, a 100-gigawatt laser array the size of a city firing at a sail. And then, in July 2025, an astronomer at Columbia published a paper describing something that weighs 3.5 pounds. No engine, no fuel of any kind, no laser, a ribbon of carbon thinner than a soap bubble that sits in sunlight and slowly spins itself up like a child winding a sling, and then lets go. Made of materials you can order today from a commercial supplier. It sounds like a joke at the expense of everything above it. It's not a joke. It's peer-reviewed. The arithmetic holds, and the reason it works comes down to one idea that nobody had put together in quite this way before. To understand why a ribbon can beat a rocket, you have to see exactly where rockets fail, because it's not where most people assume. A rocket works by throwing mass backwards. The faster you throw it, the more speed you get per pound thrown. Chemical rockets throw their exhaust at around 2.5 miles per second, which is fixed by chemistry and cannot be argued with. To go faster, you throw more mass, which means carrying more fuel, which means a heavier vehicle, which means you need more fuel to move the fuel. The consequence is brutal and counterintuitive. Getting a spacecraft to 10% of light speed with chemical propulsion would require a fuel tank larger than the observable universe. That is not a theoretical flourish. It is what the equation returns when you put the numbers in. You can soften the problem. Staging helps, which is why every rocket sheds empty tanks on the way up. Nuclear thermal propulsion roughly doubles the exhaust speed, and fusion designs would do far better still. But none of it changes the shape of the curve. It changes where on the curve you sit. Even a fusion rocket, a technology we have been 30 years away from for 70 years, lands you at a few percent of light speed at best, and only if you accept a vehicle the size of a battleship built in orbit. And every one of those designs shares the same original sin. The energy source rides along. You're not just accelerating your payload, you are accelerating the thing that does the accelerating, and the tank it sits in, and the shielding around it, and the structure holding all of that together. So the entire field of interstellar propulsion is really the study of one question. How do you accelerate something without carrying the stuff that accelerates it? There is one obvious answer, and it has been on the table since the 1920s. Leave the energy source at home. Light carries momentum, so if you make something light enough and shiny enough, sunlight alone will push it. No tank, no engine, no exhaust. A sail. and the power available is genuinely good. At the distance of Earth, every square meter facing the sun receives about 1.38 kilowatts. Hold that power steady and you could push a gram-scale sail to 10% of light speed in 20 years using nothing but the sun. No lasers required. The catch is in the phrase, hold that power steady, and it is the catch that has crippled solar sails for a century. Quick thing before the physics gets good. If you want more of the version where we actually read the paper, subscribe and turn on the bell so the next one finds you. Because here is the thing about a solar sail that almost nobody tells you, and it is the reason the idea has sat half dead for 100 years. A solar sail can never reach even 1/20th of 1% of light speed. Not with better engineering, not with more time, not even with infinite time. There is a hard ceiling built into the physics, and every solar sail ever proposed runs into it. Work out why that ceiling exists, and the solution falls out almost by itself. Start a sail at rest, facing the sun. Radiation pressure pushes it outward. It accelerates. So far, so good. But as it moves away, the sunlight falling on it weakens. Double the distance and the intensity drops to a quarter. Triple it and you are down to a ninth. The sail is running away from its own power source, and the further it gets, the less push it receives. Integrate that over an infinite distance and you get a finite answer, which is the whole problem. A sail released at Earth's orbit tops out at about 0.04 of 1% of light speed, no matter how long you wait. At that speed, the nearest star is a 20,000-year trip. Better than Voyager and nowhere near good enough. This is why Breakthrough Starshot exists. Announced in 2016 with $100 million behind it, the plan was to stop relying on the sun and build our own, an array of lasers totaling 100 gigawatts aimed at a gram-scale sail, accelerating it to 20% of light speed in a few minutes. That gets you to Alpha Centauri in about 20 years. The physics of Starshot is sound. Nearly a decade later, the project has not launched anything, and the obstacle is not physics. 100 gigawatts is roughly the entire electrical generating capacity of Germany, focused into a beam, held steady on a target the size of a postage stamp traveling at relativistic speed. The cost estimates are in the hundreds of billions. Nobody's going to write that check. And the cost is not even the only wall. The sail has to survive 100 gigawatts hitting it without vaporizing. It has to stay perfectly centered in the beam because drifting a few centimeters off axis at that power level destroys it. The beam has to be corrected in real time for atmospheric distortion across an array kilometers wide. Each of those is a research program in its own right. So, the field arrived at a strange impasse. The sun gives us free power forever, but the sail runs away from it. A laser solves that, but costs more than a war. Unless you could somehow keep the sail from running away. Here is the insight the whole paper rests on, and it is small enough to explain in one sentence. If the sail cannot move away from the sun, then do not let it move. Let it spin instead. Think about what a flywheel is. It's a battery made of motion. You put energy in slowly over a long period. It stores that energy as rotation, and then you take it all out at once. Your car has one. NASA has experimented with high-performance versions that hold nearly 2 megajoules in a spinning disk. Now apply that to sunlight. Instead of letting radiation pressure push a sail outward, where the light gets weaker and the acceleration dies, you use the same pressure to make something rotate in space. The object stays exactly where the sunlight is strongest. It never runs away from its power source, and rotation accumulates. The inverse square law, which killed the ordinary sail, simply never gets to act. You have taken the one weakness of solar sailing and engineered around it, not by finding more power, but by refusing to leave the place where the power is. Then, when the thing is spinning as fast as it can survive, you let go of the payload at the tip. All of that patiently gathered energy, months of years of sunlight, delivered into a chip in a single instant. The strange part is how ordinary the ingredients are. Radiation pressure has been understood since Maxwell. Flywheels are older than the Industrial Revolution. Nobody was waiting on a discovery. The pieces were sitting in plain view for a century, And what was missing was somebody asking whether the sail had to travel at all. It's a sling, the oldest weapon humans ever built, scaled to the solar system, powered by starlight. Which raises the obvious objection, and it's a good one. If sunlight is pushing on this thing hard enough to spin it, sunlight is also pushing it outward. So it drifts away, the light weakens, and we're back exactly where we started with the ordinary sail. That objection is correct. It would sink the entire idea. And the answer to it was invented 6 years earlier by the same person for a completely different reason, with no idea it would ever be useful for this. The design is called TARS, which stands for Torqued Accelerator using radiation from the sun. The acronym is also deliberately the name of the robot from Interstellar, which tells you something about the spirit of the thing. It was published in July of 2025 by David Kipping and Kathryn Lampo at Columbia. Physically, it could not be simpler. Two thin surfaces joined together facing the sun. One side is coated in silver, the other is dark. That's it. The silver side reflects the light that hits it, and reflection delivers roughly twice the momentum that absorption does. So the bright half feels about double the push of the dark half. Arrange the two halves in opposite phase, and the imbalance becomes a torque. The whole structure starts to turn, and it keeps turning, and every second of sunlight adds a little more rotation. If that sounds familiar, it should. It's a Crookes radiometer, the little glass bulb with black and white veins that spins in a sunny window. Except the toy actually spins the wrong way, driven by air currents rather than light. In vacuum with no air to confuse things, the effect runs in the direction the physics says it should. Now the objection from a minute ago. The whole assembly does feel a net outward push, and left alone, it would drift. The fix is something Kipping called a quasite, which he came up with in 2019 while working on an entirely unrelated problem. To understand it, you first need the older idea, the statite. A statite is a sail so light and so reflective that the outward push of sunlight exactly cancels the sun's gravity. It does not orbit. It just hangs there, motionless, held up by light. A quasite is the deliberately imperfect version. It is thin and shiny, but not quite enough to cancel gravity completely. So it still falls inward, which means it needs some sideways motion to stay up, which means it orbits. But because light is carrying part of its weight, it can orbit far more slowly than Kepler's laws would allow for an ordinary object at that distance. It circles the sun at an eerie, impossible-looking crawl. And that's what holds TARS in place. It can't drift outward because gravity still has the upper hand. It can't fall in because it's orbiting. It sits at the distance where sunlight is strong and spins and waits. An idea invented in 2019 for no particular reason turned out 6 years later to be the missing component of something else entirely. That happens more often in physics than anyone admits. This is the part where most coverage of TARS gets carried away, so let's do it properly. The design in the paper is a tapered ribbon 207 feet long and 23 feet wide, made of carbon nanotube sheets sprayed with nanostructured silver, about 2.5 microns thick. Total mass 3.5 pounds. Both materials are commercially available right now. Nothing in that sentence requires an invention. It spins up at the distance of the Earth until the tips are moving at about 7.5 miles per second, which is the point where centrifugal force exceeds what carbon nanotubes can hold. Any faster and it tears itself apart. Add the orbital motion it already had, and the payload leaves at roughly 25 miles per second. That is above solar escape velocity, so the chip is genuinely leaving permanently. Now the honesty. 25 miles per second is about 2.5 times Voyager 1. It's not relativistic. It's not close to relativistic. A probe leaving at that speed reaches the nearest star in something like 50,000 years, which is an improvement on 75,000 and still not a mission anybody alive will see the end of. The figure you may have seen quoted, 620 miles per second, around 0.3% of light speed, does not come from this design at all. It comes from a different one. In that version, the ribbon is replaced by paddles that carry an electric charge. and the theoretical maximum for that configuration is around 1,000 kilometers per second. No exotic orbit, no Earth maneuver, no gravity assists. A different machine entirely. Both numbers are real, they simply belong to two different builds, and anyone showing you the big one as though it comes out of the box is selling something. Kipping himself is blunt about this. He calls it, in his own words, not a silver bullet, and points out that it launches chips, not people. The G-forces at release would liquefy anything biological. So what is it actually for? It is a demonstration that the cost floor of interstellar exploration might be 4 orders of magnitude lower than everyone assumed. Starshot needs a national budget. This needs a satellite launch and some patience. You could build 100 of them for the price of one ordinary space telescope, fire them in different directions, and simply see what comes back over the following centuries. There is a part of this story that does not usually get told because it happened after the headlines moved on. Kipping published the paper explicitly asking for the community to take it apart. Within 2 weeks, they did. The interstellar research community ran the design through public analysis, and alternative versions started appearing. Modifications to make it spin up faster, a more complex rotating tether launcher offering more flexibility, arguments about release mechanisms and mission design, debate over whether the tapering is optimal. None of this is embarrassing. It is the thing working correctly. A concept published in July was being iterated on by strangers in August, which is roughly the opposite of how the $100 million project has gone. And it points at something worth noticing about how progress actually happens here. Starshot was an attempt to solve interstellar travel with money. TARS is an attempt to solve it with a trick. The trick may not be enough, but tricks are cheap, and you can try a lot of them, and you only need one to work. Step back and look at what this actually is. Every serious interstellar concept for 60 years has been an exercise in more. More energy, more mass, more money, more infrastructure. Antimatter factories, fusion drives, laser arrays drawing the power of a nation. The assumption underneath all of them is that crossing an impossible distance requires an impossible machine. And then somebody points out that you could do a smaller version of it with 3.5 pounds of carbon film, a coat of silver, and the patience to let sunlight push on it for a few years. Not because he found new physics, because he asked a different question. Not how do we build the biggest possible thing, but what is the smallest thing that would still work? There's something almost insulting about the elegance of it. We spent decades imagining engines the size of cities, and the answer on the table is now a sling. The same principle a shepherd used 5,000 years ago, spinning a stone faster and faster, and then letting go at exactly the right moment, scaled up until the stone leaves the solar system, and the arm doing the spinning is made of light. It will probably not be the design that gets there. Most first attempts are not. But it moves the conversation from something that requires a civilization to something that requires a grant. And that is a change of category, not a change of degree. So, the question worth arguing about below is this one. If you had 100 of these, cheap, launched in 100 directions, and none of them would report back within your lifetime, would you build them anyway? Is it worth doing something whose entire payoff belongs to people you will never meet? Or is that exactly the kind of thing a species has to be willing to do before it deserves to leave? And if a 3.5 pound ribbon can move a chip between stars, the obvious next question is, what would it take to move the entire sun? Watch why we can't build a star engine yet. It's on screen right now.